Hello students, welcome to the electrical engineering channel. In this lecture, I am going to extend my discussion on synchronous motors. The previous lecture was based on basic introduction, design and working principle of synchronous motors, and in this lecture I will discuss the effect of increased load with constant excitation and the effect of increased excitation with constant load on various parameters of synchronous motors using phasor diagrams. So in the first part, increased load with constant excitation will be discussed, and the first part is a normal excitation. And in normal excitation, we mean that the back EMF is equal to the applied voltage, as we can see in this phasor diagram. This is the applied voltage which is taken as a reference, and this is the back EMF. And we can observe that the magnitude of back EMF and the applied voltage are same, or this can be observed by the length of these two vectors. So the length of this voltage vector and the length of this back EMF vector, they are equal. So first we will consider uh, one load. So initially the back EMF is EB1 and the angle is alpha 1, and alpha 1 is the load angle, and this is the applied voltage. So whenever we increase the load, this angle alpha 1 increases, and when we decrease the load, this angle alpha actually decreases, and the length of this back EMF vector remains the same. And when we increase the excitation, the angle remains constant and the length of this back EMF vector increases or decreases, and vice versa. So now we are increasing the load, says, so the length of this back EMF vector will be same, and the load angle will increase from alpha 1 to alpha 2. So the back EMF vector will adjust itself in this direction with the same magnitude or the same length of the vector. So in order to determine the reactance voltage from this back EMF, we have to place this back EMF vector over here, so that the head of this back EMF vector lies on the head of this applied voltage vector, and this back EMF vector should be rotated or should be 180-degree shifted. So this will become EB1 dash. So this is back EMF oriented in this direction, and EB1 dash will be oriented in this direction, and their heads will be lying on top of each other. So the tail uh, of this applied voltage vector will be joined with the tail of this EB1 dash vector, and this new vector will be termed as ER1, and it will be the reactance voltage. So for the first load, when or for the reduced or small load, we will get this ER1 vector, which is represented by the black colored vector, and similarly we will repeat the same procedure for this EB2. So EB2 dash will be drawn over here, and it will give us new ER2 vector. So this is ER1, this is ER2. So clearly we can see that ER1 is lying in this direction and its magnitude is small. ER2 is lying in this direction and its magnitude is large. So from this ER1 and ER2 we can plot the armature current vector. So this will be IA1 and this will be IA2 vector. Now IA1 and IA2 vectors will be lying at almost 90 degrees with these ER1 and ER2 vectors respectively, and this will be the magnitude of EA1. So when the magnitude of ER1 is small, the magnitude of IA1 will also be small, and when the magnitude of ER2 is large, the magnitude of IA2 will also be large. So these are the new angles. This angle is phi 1 and this angle is phi 2. So this is how the quantities change their phases and their magnitudes whenever we change the load. So this is the summary of all the quantities which have undergone a change as a result of load variation. So when we increase the load and keep the excitation constant, the load angle increases, the reactance voltage increases, the magnitude of armature current increases, the angle between IA and V actually this also increases, but the excitation remains constant. Uh, so due to this reason, the back EMF also remains constant. So it doesn't change and all other quantities increase. So this actually happens when we have normal excitation or when the back EMF is equal to the applied voltage. So now we will discuss the case when the back EMF is smaller than the applied voltage, and then we increase the load, and then we will see how other quantities actually change. So this is the case when back EMF is smaller than V, and this is called under excitation case. So in this case, you can see that this back EMF vector, its length is smaller than the applied voltage vector. So this is black vectors are actually the first vector, and these red vectors are the vectors after the increment of the load. So this is EB1, and we will place this EB1 vector over here, and it will become EB1 dash. So this is the dashed line, and this is the ER1 vector. Similarly, when we increase the load and keep the excitation constant, the angle of this back EMF vector increases, but its length remains the same. So this is new alpha 2, and according to this EB2, we will place this EB2 dash vector over here, and this will be the resultant reactance voltage. So clearly, the reactance voltage magnitude has increased, and the reactance voltage angle has also increased with this applied voltage. So in this case, we actually had ER1 in this direction, but ER2 was rotated clockwise. But in this case, we have seen the opposite phenomena. The ER2 magnitude has although changed, but ER vector actually has rotated in the counterclockwise direction, and its magnitude has increased. So due to this reason, this will be the EA1 at the smaller load, and after the increment of the load, this is the new armature current vector IA2. So this is IA2, and its magnitude has increased since the magnitude of ER2 has increased and its angle has decreased. So this is a summary of the results when we increase the load under excitation case. The load angle increases, reactance voltage increases, armature current increases, but phi 2 actually decreases, and EB1 and EB2 they are the same. So only this quantity has decreased and all other quantities have increased, and the back EMF remains the same. So in the final case, we will discuss the overexcitation case in which the magnitude of this back EMF vector is greater than the applied voltage vector. So this is the applied voltage vector V. This is EB1 at an angle of alpha 1. When we increase the load, this is EB2 at an angle alpha 2, but the magnitudes are same since the excitation is kept constant. So this EB1 has to be placed over here. So this is EB1 dash, and this will become ER1. Similarly, this is EB2, so this is EB2 dash, and as a result, this will be the ER2 for excitation voltage vector. And now the uh, reactance voltage magnitude has increased again, and it has shifted clockwise in the clockwise direction as we observed in this case, and its magnitude has increased. So due to this reason, this will be the IA1 vector, which is lying at almost 90 degrees with ER1 vector, and its magnitude will be small since the magnitude of ER1 is small. And this is ER2, and IA2 will be also be lying at an angle of almost 90 degrees. So this is IA2, and its magnitude will be greater than IA1. And this is the phi 1, and this is new phi 2. So phi 2 has increased, and phi 1 was greater, and phi 2 has decreased. Now these are the angles which are corresponding to the leading power factor regime. So this is a summary of the results. And under over excitation case, the load angle increases, the reactance voltage increases, the armature current increases, but this phi phi angle actually decreases, and this back EMF remains the same. So these are all the results. So from this discussion, it is evident that the variation of these quantities for a load variation actually takes place in a different way for different excitation cases. So for normal excitation, when we change the load, these quantities will change differently. For under excitation case, when we change the load, these quantities will undergo change differently. And for over excitation case, when we change the load, the quantities will undergo change differently. Now we will discuss the case when we have constant load and we vary the excitation. So again, this is also going to be a very important and a technical discussion. So we will start our discussion assuming that we are already running the motor for over excitation case, and we are achieving unity power factor from the motor. So unity power factor means these armature current vector and the supplied voltage vector, they will be in phase, and this will be the orientation of the reactance voltage, and this is the back EMF at an angle of alpha 1. So EB1 dash will be lying over here, and this will be ER, and this is the direction of IA, and they are in phase with each other. So we have unity power factor. So in this case, if we ignore the stator copper loss, the mechanical power will be equal to the input power, and in this case input power is equal to voltage into armature current multiplied by cos of angle between them. Since they are in phase with each other, so cos of angle between them will be equal to 1, so the mechanical power will be equal to V times Ia. So this is also equal to the load power if we ignore all the core losses and the rotor copper losses. Now, this is our base scenario, and from this base scenario, we will extend our discussion after first reducing the excitation and then increasing the excitation. So, when we reduce the excitation, the length of this back EMF vector will decrease initially, which we can observe in this phasor diagram, and we have kept the load constant, so the load angle will be same as alpha 1. So, this is EB1, and according to this EB1, we will evaluate EB1 dash, so which is plotted over here, and this is our new ER1. And when we have such ER1, the armature current will also undergo slight deflection and it will be directed downward. So in this case, ER1 will be ER1 was at the y-axis and IA was at the x-axis. When ER1 is lying over here, IA1 will also deflect downward. Now this is IA1, and if we have kept the load constant, the mechanical power available under this condition will be smaller than V times IA1. So V times IA1 is actually this the product of this applied voltage, which is constant, and this is the armature current vector. And in this case, the armature current vector is IA1 and it is deflected downward. So first we have to evaluate the horizontal component of this IA1 vector, and that component is equal to V times IA1 cos phi 1. So the horizontal component of this armature current is actually the component lying from here up to this point, and this IA1 cos phi 1 is much smaller than this IA1. So under this condition, the power generated by the synchronous motor is equal to V times Ia1 cos phi 1. Since Ia1 cos phi 1 is much smaller than Ia in this case, so it means the motor has to draw more power from the supply. Since the load is constant, so the it should produce the power which is equal to V times Ia. So now the motor will reorient its back EMF vector, and the new back EMF vector will be directed in this direction, and its magnitude will also be higher. So as a result, this EB2 dash will be lying over here, and we will get new ER2 vector. So this was ER1 vector, new ER2 vector will be directed over here, and according to this ER2, we will evaluate IA2. So IA2 will be lying at almost 90 degrees with ER2, and this is our IA2 vector with a new angle phi 2. Now the horizontal component of this IA2 vector is IA2 cos phi 2, and the horizontal component of this vector is the vector starting from this point up to this point, and the horizontal component of this IA2 vector is exactly equal to the IA vector in this figure. So in this case, VIA2 cos phi 2 is exactly equal to V times IA, which we can observe from these two figures. So this will be the new direction of all the vectors as a result of the reduced excitation. So normally we have the perception that whenever we vary the excitation, the load angle remains same, but the back EMF magnitude varies. But when we are running the motor at constant load, then as a result of reducing the excitation, the mechanical power generated by the motor will be small, and then motor has to extract more power from the supply to satisfy the load. Since the load is constant, so motor has to reorient all of its vectors, including the back EMF vector, the reactance voltage vector, and the armature current vector, so that the horizontal component of this armature current times the applied voltage is equal to the voltage times IA vector in this case. And now this is the new direction of all these synchronous motor quantities. So this is also written over here. So initially V times IA1 cos phi 1 is smaller than V times IA. So this will not be the steady state of the synchronous motor, since it has to supply the power which is exactly equal to V times IA. So it will reorient all of its vectors, and the new vector will become IA2, phi2, ER2, and EB2, and V times IA2 cos phi2 in this case will be exactly equal to V times IA, since the horizontal component of this armature current vector is equal to IA2 times cos phi2, and its length is starting from here up to here. And this is exactly equal to IA in this figure. So this is the new mechanical power, and it is exactly equal to V times IA. Now in the second case, we will increase the excitation under constant loaded condition. So when we increase the excitation, the length of this back EMF vector will increase from this EB. So this is the base scenario in which we have back EMF vector as EB, and when we increase the excitation, initially this back EMF vector will grow larger, and as a result of this EB1, we will evaluate ER1. So EB1 has to be placed over here and naming it EB1 dash. So this is our ER1, and according to this ER1, we will have this IA1, and this IA1 is lying at almost 90 degrees with ER1. Now the horizontal component of this IA1 is much greater than this IA in this case. So the horizontal component of this IA1 is actually the component starting from this point up to this point. And this component is greater than IA, which is starting actually from here to here. So now again, motor will reorient itself, because in this case, the motor is generating excess power as required by the load, which is equal to V times IA. So it will decrease the magnitude of its back EMF, and it will reorient this back EMF vector in this direction. So alpha 2 will be smaller now. The magnitude of EB2 will also be reduced, and EB2 dash will be lying over here. And as a result, this will be our new ER2, and this will be the direction of IA2, and this is the new angle phi 2. And since this is IA2, its horizontal component will be IA2 cos phi 2, and IA2 cos phi 2 will be starting from here up to here, and exactly this is the length of this IA vector. So now the motor will be generating power of V times IA2 cos phi 2, and this power is exactly equal to V times IA. And initially the motor was generating power V times IA1 cos phi 1, which was greater than V times IA. So after doing these vector reorientations, the motor will be stabilized with these red colored vector orientations. So I hope you have understood the concepts which have been discussed in this lecture. So for watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.